Hello, friends. It's good to see you. More of you today than last time. Welcome back. To those of you who are just joining us. Teresa, how was Boston?
I put it mild disease because I don't like hypothermia.
Good call. I don't like hypothermia. Hyperthermia? Hypo. Hypo, the cold kind, right? Yes, I don't like that either. Good call. Yeah, I saw some of the pictures and it looked like horrible. Like just Yes, yes. Well, welcome back. And everyone else is back from conferences and such. Yes. My husband finally made it back from New York. He was stranded there on Monday. Had to miss class and such. And I was very happy, of course, to not be a single parent anymore. I wanted to show you the picture of pure happiness. This is Kiwi on Tuesday morning. Hey, open it up with, no, just open it with that. Okay. This is the picture of pure happy. Nana sent him a Paw Patrol sweatshirt in the mail for all of his recent successes in putting poops in the potty, which has been such an ordeal, I can't even tell you. But he's got it down now, and he's so happy, and I'm happy for him. So let's give it up for Huey. Yay, Huey. See, I'll show this to him later. Like, why they are clapping, Mommy? I don't get it. Because everyone wins when we put poops in the potty. That's the moral of the story. This is the world of being Dr. Mommy, right? This is my split personality. So on the doctor's side, a couple of announcements here. I did get the video fixed from Monday. What happened is that I posted it before it was all the way done processing, and so it showed only the first half hour for a while until it caught itself up. So that looks to be fixed. You have a new handout that I'm not sure if we'll get to today, but I wanted to put it up just in case we do get that far. And I did update the point totals down here to reflect that we've lost one homework, and the number of total possible homework points is now 78 instead of 88, which means your last one will be worth 12. And there is one more quiz yet to do next week, and then you'll have everything. The last homework will be due at the end of finals week. Current homework that's out right now on Logit models is due Friday. Any questions on that? Our usual place to start. Yes, Jacinta, help me. Go ahead. The test statistic of it. So I've had a couple of questions that have been asked repeatedly, so that is one of them, because in the original version of the binomial example, which was example 7C, I had a typo for this model too that had an empty means two-level random intercept. I had an extra dot in there, which is what's necessary to test the over-dispersion parameter in the next model. That was just a copy-paste error. So if you have an extra dot, that might be what the problem is. The extra dot was originally right here in the empty means two-level random intercept binomial model. It's the second model in example 7C. And that dot should not be there. So you should have only a 0 in that statement, which means take the random intercept variance and remove it from the model and estimate it and see what the difference would have been. So this is how that should look. You're not doing over-dispersion in the homework, so you don't have to worry about that. The other thing, making sure folks are using the right DV. I gave it to you directly in your new data set, so it should be n thumb over n total, which is just a renamed version of what this generic name is right here that fits our example. And last but not least, I've seen this several times. In this example, the next thing that I did was do saturated means by wave. That's the ANOVA version of the model in which each occasion gets a separate mean. And I accomplished that by taking this wave variable, which was on the class statement, and putting it in the model, so it's being treated as categorical. If you tried to do this in your homework, you probably got a message that SAS was very angry with you, and there was insufficient memory to do whatever you were trying to do. So your next model after an empty model should be having a linear slope for time, in which case whatever time variable you've created that's centered such that the first occasion is 0 does not go in the class statement. So in general, what goes on random and model are the continuous versions of time, unless you're trying to estimate a saturated means model, in which case the time variable goes on class. It cannot go on random, though, because that model won't be identified. So, other questions? Erin?
For the difference in the linear time slope,
Mm-hmm.
so we're writing an estimate statement.
One could.
Is that the way to do it?
Yes. But assuming one is writing an estimate statement, what is your question?
Well, I put time as 1.
Mm-hmm.
But then I couldn't figure out how to.
In this case, you're not estimating a linear slope for a particular group. If you were doing that, it would be time 1, and then you tell it for which group. If you're estimating the group difference in the linear slope, that is the root of the equation. It would be the group difference in the linear slope refers to what as an idea? You can phone a friend. You can make someone else answer for you if you want. Time by group. Yes, exactly. So that's the thing you're trying to estimate that would get the 1. And then there's nothing else, which is why I said one could use an estimate statement, or one could do what instead? Stare at the output you already got, because it's group by time. If that's the only thing you need, that shows up as a fixed effect. You don't need the group difference in the linear slopes conditional on week. So let's look at the wording of the questions of interest here. This is section 3. So we're asking for the predicted intercept at these specific weeks, as well as the group difference in the intercept for these specific weeks. The slopes, though, are right here. So the predicted rate of change for each group and the group difference in the predicted rate of change per week. So that's not conditional. You couldn't. Which?
I'm talking about that one.
Wait. This is the one you want? We're talking about number 25? And the differences per week. Okay. So the differences per week are in the intercept. So you want to think about group difference as the root of the estimate statement. That's the thing that gets the 1. And then you would have how that group difference is moderated by time as the next term. So there shouldn't be anything in your estimate statement that doesn't have group in it, if group difference is the thing you're trying to get. What else can I help you with? Depends. If you're using the class statement for group, then yes. Other questions, folks? Go ahead.
Can you explain one more thing about second variable in the class statement and
For the time variables, you mean? Okay. So in the example 7C, if what you're trying to estimate is a saturated means model for time, where each occasion gets a different mean, that's when your time variable goes in the class statement. Otherwise, it only needs to go in the class statement if you're using a repeated statement, because then they pair together, but these models don't have a repeated statement. So in your example, there's never a point at which I asked for a saturated means model, and so your version of time will never need to be in the class statement. You can choose to put program in the class statement if you'd like. So if you followed my example in terms of creating a new text variable that has the group names so that you can keep track of them easier, then that group that's a text variable, a string variable, has to go in the class statement. Otherwise, you could have taken program, subtracted 1, and it would have turned into a program variable that is 0 versus 1, and then you wouldn't need a class statement. When you use a class statement, though, its reference group is the last alphabetically or the highest numerically. So like if you named your groups teeth and maturity, teeth is the reference because T comes after M. In this current example, SLI is the reference because S comes after N. So, does that help? Okay. What else can I help you with? Nothing? I can't help with anything? You're completely self-sufficient? Excellent. Good to hear. Well, I will shut this down. Don't need to save that. And in looking at the schedule, the same thing is happening that happened at the end of 9:45 last time, which is that the multivariate section keeps getting compressed as we run out of time. So at this point, I'm going to have to scale back what I had originally intended to do. I'm probably going to stick with the more modern of the examples, using multivariate models within M+. If you want to see some of the ones that you will have missed, the last version of what was called Psych 945 when I was at Nebraska in 2014 has those examples. So those would be using SAS, tricking mixed into thinking that you have a univariate model still, but you can run multivariate models using stack data that way. The only catch is that you can't look at relationships between the DVs in any way except covariances. So if you want to do like a multi-level mediation kind of thing or any of the cool stuff, SAS can't help you with that. So I will probably just end up with the latter examples here, mediation and 7 ways of estimating multivariate change. Incidentally, I am giving a workshop on some of these models at Oklahoma State University right after this class is over. I drive down on Mother's Day, and then the next 2 days I'm giving that. So they are charging some a little bit of money, but if any of you have extra money that you need to spend before the end of your grant or your fellowship or whatnot, come down to Oklahoma. We'll party there. I hear Stillwater is lovely this time of year. I'm about to find out. So the workshop is called something like Modeling with In-Person Association, but it's these kinds of models with time-varying predictors and multivariate applications such as mediation that I'm going to be talking about for 2 days. So. Oh.
So maybe bring like
Okay. I will add great. That sounds like fun.
Yeah.
Well, great. Okay then. So maybe don't come to Stillwater. I've never been. Hopefully. Well, thanks for the heads up. I will be checking the fire weather report in addition to the temperatures then. So, I'm giving an introductory workshop at the University of Illinois the first weekend in May. So if you have any friends at the university in Champaign-Urbana, tell them to come on by as well. So that's enough self-promotion for right now. Any other logistics or homeworks questions before we dive back into 3-level model land? No? Okay. Then away we go. So 3-level models. Partitioning variants that used to be 2 levels into a 3rd level. And the way that one would approach this in terms of what makes the most sense depends on the kind of design. So in this current example that we've been talking about, it's for what's called clustered longitudinal data, people who are nested in groups and the people are followed repeatedly over time. So in that case, we would tend to assume by default that we need at least a 2-level model for occasions within persons. It would be a potential empirical questionness, let's make up some words there, as to whether the people are nested in groups such that you need to control for group. So fixed effects or random effects would be your options for doing that. In the case of twin studies, yes, most certainly we will need to control for group. So we talked about different kinds of 3-level designs. We talked about notation a little bit. The big change in notation is the existence of another set of placeholders. So it used to be that we had our fixed effects at level 2 and our random effects at level 2. Now level 2 still has any potential level 2 random effects, but where the fixed effects used to be is going to be a system of placeholders that talk about what the term will become at level 3. And as I said on Monday, I think my bad for picking V for the level 3 random effects, given that the V matrix is already another thing. So do you want to review partitioning? Would that be helpful? Why not, right? We're here. So we have my schematic here for two-level models. Once upon a time, there was an E. We split it into what was between persons, or between something at level 2, intercept variance, versus what is still E at level 1. In a three-level model, for, say, clustered longitudinal data of time within person, within groups more generally, same idea. We start with what is E versus U at level 2. So we're differentiating how much of the total variation is at level 2 or higher, is cross-sectional, is between persons. And we can calculate an intra-class correlation for the proportion of variance that is between over total, the same way as usual. But if we've only modeled level 2 variation in the intercept, what's still embedded in it is any higher level variation that we haven't put in the model yet. So it really is 2 plus anything else that's lurking there. So in a three-level design then, we split out how much of that level 2 intercept variance is actually level 3, is actually between groups versus level 2, which becomes within groups. And that split affords us another kind of intra-class correlation, which I call the intra-class correlation at level 3. So relative to just the 2 and 3 variance, how much is 3? It's the effect size for how important this second split is. So ICC level 3 gives us the expected correlation of people from the same group with respect to their intercepts. ICC level 2 gives us the expected correlation of occasions from the same person and necessarily the same group. So here are the formulas then that convey those two ideas. There are lots of different kinds of intra-class correlations possible in 3 and 4 and 5 level designs. The ones that make the most sense to look at are going to be context specific. So in this case, I'm starting with a default assumption that we need to at least differentiate longitudinal from cross-sectional variation. That's the first one here. So in a 3-level model, the ICC for level 2 is a function of the level 3 random intercept plus the level 2 random intercept over all the variance, level 3, level 2, and level 1. So if you haven't split 2 from 3 yet, then functionally all of this level 3 variance is actually still in level 2. So we saw that in the example with the longitudinal twin data, where we had our first model that is a 2-level model of time within person, ignoring the fact that we have twins, treating people as independent, and the intra-class correlation at level 2 then was 0.85. So right now it thinks that all of the between-person variance is 136, which is 85% of the total variance in this outcome. In then transitioning from a 2-level model to a 3-level model, its job was to take that 136 that it thought was between person and split it into what is actually between families and within families. So that 136 then becomes 87 versus 49. So, and then looking just at that latter split, of the variance that is level 2 and higher, how much of it was actually level 3? That tells us about the extent of dependency of people from the same group and the average correlation of people from the same group. So if you have twins who are identical in their behavior, there's absolutely no difference between twin 1 and twin 2 in a pair, what's my ICC level 3 going to be? 0 or 1? If I have absolutely no differences between the two twins within a pair, they are the same. 1, such as their age, right? By definition, twins are the same age. So the intraclass correlation for a person's age at baseline is 1, because twins have all shared variance in age, no unique variance within the pair. If instead we're talking about an outcome in which how one twin does has nothing to do with how their sibling does, that creates a level 3 interclass correlation of, say it with me, not 1, 0. So yes, this is the effect size that conveys how much we need a 3-level model versus a 2-level model. ICC level 2 conveys how much we need at least a 2-level model relative to a single-level model. And we'll skip this one again for now and talk about slopes then. So before we do that, looking back at the code, just to remind you, how you tell what level is which is guided by the subject line here. So pair ID means it's level 3 because it's the ID variable for the family, for the twin pair. The unique combination of pair by twin creates level 2. So it's not a literal multiplication because that wouldn't work in this case. It's more like a pairing of ID variables together. So upon adding that 3rd level, we get a significance test for whether the model fit improved via our usual -2 log likelihood difference. That is significant. The effect size for that 2 versus 3-level model comparison is your ICC level 3. So we have, out of the total variance, that's 161. The level 2 interclass correlation is still 0.85. So 85% of the total variation is level 2 or higher, is between persons, is cross-sectional. And then within that between person level 2 or higher cross-sectional variance, how much of that is due to family, is due to shared information between the twins, is 64%. So it's 64% of the 85%. How we doing? With me? All right. Any questions on that much or any of that that you'd like to hear again? It's just one column for pair and one column for twin. Pair is just a standard ID variable. Twin is just 1 versus 2. I didn't have to create a new variable for SAS or SPSS. I did have to create one for the very first model in Stata because of the way that its syntax is structured, and I called that case. So you could create a unique ID for each person. You don't necessarily have to. That can be useful for other data management purposes. All right. So then we looked at time in the same way, did a 3-level model for time to see how much of the variance is between persons because of how old they were when they started versus within persons, which is how long they were in the study. It's 63% at the family level and 37% at level 1. So we then created a variable for time and study. Here's my saturated means model that gives me a sense of what time is going to need to look like. Looks a little bendy. So then we added fixed linear and fixed quadratic time at level 1. Here's my notation for that at model 2A. So the level 1 model now has 3 beta level 2 placeholders. There we go. Intercept, linear time, and quadratic time. And I'm describing what time means by the terms in parentheses. It's how old you are right now minus how old you were when you walked in the door, otherwise known as time and study. Each beta then gets a level 2 equation, each of which is starting off with a placeholder for what the term is going to be at level 3. Only the intercept has a random addition to it at level 2. And then level 3, each of these delta, that's what this squiggly thing is here, these delta placeholders gets its own equation where the fixed effect goes in, fixed intercept gamma 000, fixed linear time slope gamma 100, fixed quadratic time slope gamma 200, and then here's my random intercept for the pair V right here. And because time is level 1, if we were to look at pseudo R square, which I think is about where we ended up with the example, it explained 8.33% of the residual variance, and anytime you reduce residual variance but not anything else, the intercept variances will go up as a consequence. And then I started singing again, and we were talking about slopes. Is that about it? A good recap? Okay. So now the same idea with the slopes. In a 2-level model, after this first partition into what is level 2 intercept variance versus level 1 residual, we add fixed effects of time. That explains residual variance. And then we can talk about whether those effects of time need to be random over level 2 units, which is persons here. If so, then what used to be E level 1 residual variance, why are you off your line? Part of that is because of individual differences in the slopes of the lines. Why are you off your line? Well, maybe because you need a different slope than everyone else. So that level 1 variance, part of it becomes level 2 variance. It's level 2 variance in the level 1 effect of time. So the level 1 effect of time can vary randomly over level 2 people. And the final version then would look like this in the boxes, where I have a level 1 residual variance, which is why are you still off your line, even though you have your own line. I have why do some people change differently, and why do some people start off differently. Slope variance and intercept variance, because both of those terms are at level 2, which is between persons here, they get a covariance. Now, same story in a 3-level slope model. Just as we took this level 2 person intercept and split it into what was actually between groups versus within groups across persons, we can do the same thing for the slope. So we get a person slope first. We allow individual differences at level 2 in the level 1 effect of time. Next question then, how much of those individual differences in the effect of time are common to the group, are shared? Do some groups, on average, change more or less than other groups? To the extent that that's the case, we will need a group slope variance as well as a person slope variance. So the final version of what's in the model then is in boxes here. Level 1 residual, which is still why are you off your line today? I have level 2, which is person intercept variance, and level 2 person time slope variance, which is why are you higher or lower than everyone else in your group at time 0. That's level 2 person intercept. Why are you higher or lower than everyone else in your group at time 0? And why do you change more or less than everyone in your group? So level 2 is within your group specifically. So you can think of it as between persons, but it might be easier to think of it as within groups. And then lastly, at level 3, why do some groups have a higher mean at time 0? Why do some groups change more or less than other groups? I don't know. We'll figure that out too. And because both of those green terms at level 3 are at level 3, they get a covariance. The level 2 terms get a covariance, but there's no covariances across levels, the same as usual. That one. Oh yeah, and then in the same logic, we can create interclass correlations that describe how much of the intercept variance is between groups as opposed to within groups, how much of the slope variance is between groups as opposed to within groups. So a random slope model where both the intercept and the slope are random at both levels would look like this. So I have 2 betas at level 1, so I've got 2 level 2 equations for beta at level 2, 2 placeholders, 2 random effects. The placeholders at level 2 then go to level 3. That's how each group gets its own intercept and slope. So the fixed effects then, the fixed intercept is the average intercept across groups. V is the random effect for how far off your group's intercept is. Likewise, gamma 100 is the average time slope across the groups. V10J is how far off your group's time slope is. Those together feed down into level 2. You pick up the U's, which then allows you to deviate from your group's predicted intercept and slope. And that then feeds down into level 1, which picks up the E, which gets you to where you are at each occasion. And the composite, when you put it all together, which I think is a little more straightforward to understand in this model, looks like this. Okay. How are we doing? So I had a hard time initially understanding how you could have a random slope at both level 2 and level 3. To me, it seemed redundant. And when I was here as a graduate student working in the Research Design and Analysis unit downstairs, the same unit that I'm now back working with again, we were lucky enough to have a speaker come and give a workshop who was Don Hedeker. I've talked about him before. And our group got to meet with him, basically just like drill him with every question that we ever wanted answered. He just sat there and he's like, okay, and then he just picked up a marker and started talking, right? It was like the best 3 hours ever. But I asked him this question: how is it that you can have a random slope at 2 and 3 and it's not somehow redundant? And he drew this picture for me. So I'm giving him full credit for my understanding of this concept. This is the way that I like to think of it. So I have what is a 2-level version of variance and slopes versus a 3-level. So if we look at this blue family here, this is what it would look like if we only had random slopes at level 2. So in this picture, the mean slope for the sample is going to be 2.0. The mom of this family, we're giving this a different kind of pair here, has a steeper slope than the average. So her slope deviation would be the mean slope here. Her deviation would be 1.5 to get up to her slope of 3.5. Likewise, the dad also has a slope that is steeper than the average, but not quite as steep as mom. And so his deviation to get up to his slope would only be 0.5. But both of these are relative to the sample as usual. Now, if we then took this model and added a 3rd level, it would instead look like this family B down here in red. So family B is not doing as well, but the idea of the variance partitioning is irrespective of sign. So they're lower than average. So the first step in this 3-level modeling process gets from the sample mean slope down to this dotted line right here, which is the family mean slope. So the difference between the grand mean slope for the sample and this family's average slope is the -1. From there, with this as our new anchor point, mom's slope is steeper than the family's average, and so her level 2 deviation is this 0.5 that's positive. Dad's slope is less steep than the family average, and so his level 2 deviation is -0.5. So the model is still trying to capture the same information. It's still the same distance between each person's slope and the main slope. It's just dividing up that distance into 2 sections. How much of it is common to both of them, as captured by the family mean slope, and then relative to that new mean as a reference point, how much does each person vary relative to their group's mean? So if you had, I'm going to have to get paint out here. There we go. So if instead, here's my average slope, I had a bunch of families where, like, here's one person in the family, And here's another person in the family. This is a situation in which adding a level 3 mean slope as a deviating point would not help. They have nothing to do with each other. So there is in the textbook a picture in chapter 10 that I drew. I don't know that I have access to it on my laptop right now, but it's figure 10.6. If you have your book anywhere near you. It's in the context of a measurement burst design, but I drew the picture to try and convey what this level 2 versus 3 meant. So if you had, let's see here, we're going to need a new picture. Back. Let's say that we have some folks that need a new color and a new picture. Hey, stop that. Like, here's one family, right? We got a lot of people in this family. And here's another family. This is a situation in which the level 3 variance would be way bigger than level 2. Whereas if you had people who were scattered, like the red family was like, here's some people here, and here's some people here, and the blue family was like, I got some people down here too, then level 3 wouldn't help you. So it's not redundant, it's just partitioning the total deviations into 2 steps rather than 1 to have a 3-level model instead of 2. But it does shed light on why you might go in the order things to do. I start with level 2. If that's significant, I then go to level 3. It doesn't make as much sense in this context to try level 3 all by itself without level 2, because level 2 is where level 3 is coming from. It has to be 2 at least before it can be 3. So here is just a depiction of the intra-class correlations for intercepts and slopes, as well as a caveat that if you want to do this, both terms need to be parallel at level 2 and level 3. So for instance, if you have an asymmetry here, let's say that at level 2 you have a random intercept, linear, slope effect, and quadratic, but the quadratic didn't have any commonality at level 3, so you didn't keep it, then having an intra-class correlation for this linear slope wouldn't make a whole lot of sense because what it means is different across levels. The linear slope at level 2, because of the random quadratic, would be the random linear slope specifically at time 0, whereas in level 3, it's the linear slope at any occasion because it's unconditional. So I don't think it makes as much sense to try and partition a term where what the term means isn't the same across levels. All right. How are we doing? Yes, ma'am.
So I just want to make sure I'm understanding this right. If there is interaction within a family where the blue and the red families are somewhere intersecting in there, then it would not be good to do a level 3?
If there's no commonality in how people from the same family change, then level 3 has nothing to do. It would be 0. If everyone in the same family changed the exact same way, then level 3 would be all of it, and there would be no level 2. Now, that is theoretically possible, but not likely in real data. Other questions? I'm sensing the energy level coming down. Do I need to start singing again? Talking about pooping in the potty or Paw Patrol or anything? No, I can tell you all about Paw Patrol. I know all the characters. He keeps getting a new character every time he tried new food, so he has most of them at this point. Yes. The other day he asked me, why I don't have Everest yet? I'm like, well, what would you like to eat? Let's get this going. And Tracker, too. That's the only other one we don't have, because those are not part of the original set. But I digress. Want to see some more models? Why not, right? We're here. So I'm adding here model 2B. I am seeing if my time slopes vary across twins, pairs, or both. Starting with random linear at level 2. So at this point, I realize that folks' energy levels might be flagging, so I'm helping you. Here's your Where's Waldo for what changed in the equation. That thing right here, U1, that's the new term. So because we've added a level 2 random slope variance, we have also added its covariance with the level 2 random intercept. So in terms of degrees of freedom for this likelihood ratio test, the shortcut that I taught you before is still valid. When you only have one thing on the line, it's like before, that's where we were. If you add another term so that now there's two things on the line, what's my degrees of freedom for the comparison? If there's two things on the line, 2. What if there's 3 things on the line, like this? 3. What if there's 4 things on the line? 4. It always works, even in a 3-level model, because it's still just the covariances with the terms at its level, which is in its line. So, and I left the spacing here to try and convey the absence of this random slope for time at level 3. So we're starting at level 2. I'm saving my info crit to do the likelihood ratio test for me. This is my notation here says random linear 2, that's RL2, and RI3 means random intercept for 3. So you can name these however you like, but I try to name them with things that mean something so that I can come back later and understand what I meant. So here are my 2 new rows. And yes, Proc Lesa is still trying to help you keep track of this stuff. So I've added my level 2 intercept slope covariance as well as my linear time variance at level 2. Usual process, do we need a random slope in the model? On 2 degrees of freedom, the model fit difference is 136, so yes. It looks like people change differently. Given the pattern of change, my guess is that they decline at different rates. That's how I would probably phrase it. And look what happened. My quadratic fixed effect is now significant. I have no ready explanation for that other than that it can happen in unbalanced data that things wiggle around. So I kept it in the model even though it wasn't initially significant because I found out later that it was. That is to say, I initially got rid of it and then realized I shouldn't have. So now I'm adding the random slope at 3. So the new term is right here, V11. So I'm picking up time right there. So what's my degrees of freedom going to be? 2. There's 2 things on its line. So now I have random linear 2, random linear 3. Here's my model comparison. Down here, on 2 degrees of freedom, the difference in -2 log likelihood is less than 1, so no, doesn't look like we need it. So this gives us an opportunity to look at intraclass correlations for intercepts and slopes to try and convey this idea of shared variance. So let's do the intercept first. How do I know that UN11 is my intercept as opposed to a slope? Because what? Because I put intercept first. I always put intercept first, but other people may not. So yes, this is the random intercept variance, and because the subject is pair, I know that that is my level 3 random intercept variance. That's 85. The analogous term at level 2, let's see if I can, no, it's not going to let me select just those, is right here. It's the 47. So we have 85 divided by 85 plus 47 to get my intercept intraclass correlation. So of the intercept variance meaning it has to be between persons. So this is not about time, variation over time. Now we're talking about between person differences. Of the total variation in intercept, 64% of it is at the pair level. Now, if I had to guess, I'd say that that's probably significant. But if I wanted to give you a p-value that goes with that 0.64, where would that come from? It's on there somewhere. Right here. 0.64 is greater than 0 if adding a level 3, or excuse me, I'm talking about the slope already. No wonder you're confused. 0.64 is greater than 0 if adding a level 3 intercept helps. And indeed, that is pretty much what we found before. So we already found that. Here's my 0.64 for the interclass correlation before. So I could have called that an intercept interclass correlation specifically. It's the same idea. Now let's talk slopes. That's what I meant to say. Here's 0.106. That is the linear slope variance at level 3. And here is 1.45. That is the linear slope variance at level 2. So this is where terminology gets confusing. This 1.4, this is a level 2 random variance in the level 1 effect of time. The level 1 effect of time varies randomly over twins to the tune of 1.4 whatever. I also have right here a level 3 random variance in the level 1 effect of time. Yep. Yes, and you can bet these are going to be drop-down questions. You can just bet. So saying these again here, 1.4. This is the level 2 variance in the level 1 effect of time. This is the level 2 random variance in the level 1 effect of time. This number right here is the level 3 random variance in the level 1 effect of time. So if I put those two numbers into the same interclass correlation type of formula, of the total variation in the level 1 times slope, only 7% of it is between pairs, is level 3, is common to the two twins. And I have in parentheses here is approximately 0 because that's what this likelihood ratio test is telling me. That 7% is not greater than 0 according to the model. So likelihood ratio tests for additional random variances give you significance tests, but you should try to convey the effect size that goes with them whenever possible. And so this is a case when it's possible to do that. Okay. Any of that you want to hear again? And the good news is that all of those words are in the back of your handout. Do you remember why? Because I don't want to write a result section, and can you make it sound more altruistic? I want to help you, and I like you. Yeah. Because technical writing is formulaic, folks. There is a pattern, so much so that I make SAS do it to generate your homework. So all I got to do is give you the patterns, give you examples, and you can go from there, and I can do something else. Yes, and you can get jobs. right? That too, right? Okay. All right. Non-significant. Is that spelled wrong, or does this word just not know that word? Non-significant. That's a word. Tell me that's a word. Add to dictionary. So, if I were going on to do other types of things besides a heritability examination, I would be inclined to drop the level 3 random slope. But this model so far assumes homogeneity of variance across twin types. So I am not accounting for potential MZ versus DZ differences in any of these shared quantities. So I'm keeping it for now so that we can talk about that later. And indeed, in previous versions of this handout where I didn't have anyone who cared about heritability in my class, I dropped it. But because folks around here do that, I say, hey, let's do it. So the next model then. I'm adding in the level 3 part of time, which is cross-sectional differences in one's age at baseline. Essentially testing whether or not people who are older start out differently or change differently. Note but here, I tested random quadratic time slopes at both levels and did not need them, so they are not here. So here's my new part. Pair age 1J minus 85. So gamma 001 right here, this is the first predictor of the level 3 intercept. The one below it here, this is actually the interaction of age by time. So it is the first predictor of the level 3 linear time slope. And because there was no random quadratic time variance, I did not add a moderator term for it. Although one could have, I decided this was enough for one example. Okay. Any of the equation stuff you want to hear again or ask me about? So note all the fixed effects in the model are sitting up here at level 3. So what is gamma 00? What's that one? See, I'm making it so you have to pay attention because it's moving. Orienting response. What's that? What's gamma 000? Intercept, fixed intercept. What is gamma 100? These are fixed. Gammas are fixed. Gamma 100 right here. Fixed linear time slope. So this is a level 1 fixed effect even though it's sitting in level 3. What is gamma 200? Fixed? Quadratic, yes. See, I'm trying to help. This is actually for my benefit as much as yours, that I've got like the Cliff Notes version of what these equations are predicting here, because it gets hard to keep track of these things when it's like, is it 10 or 01? Like, ah! Okay, so what is then gamma 001? Besides the first predictor of the level 3 intercept, you would otherwise call this I'll give you a hint. Here's my model, right? Here's my, other than the intercept, my fixed effects. We've done the fixed intercept, we've done fixed linear and fixed quadratic. So these are the two that are left. So 50-50 shot. What's this one? Gamma 001. It predicts the intercept. It's the main effect of age. Yes, main effect suggests the intercept. And by process of elimination, gamma 101 is the first predictor of the level 3 time slope. This is age by time. That's what gamma 101 is. It is a cross-level interaction. It is a level 1 by level 3. So the fixed effects are the gammas. The random effects at level 3 are the V's here. So VOOJ is the idea that each pair gets their own intercept deviation. V1OJ is the idea that each pair gets their own linear time slope deviation. So VOO is the idea of a level 3 random intercept variance. V1OJ is the idea that I have a level 3 random variance in the level 1 time slope. Level 3 random variance in the level 1 time slope. See, now you know why I pound caffeine during class, right? If I had an IV, that might be easier, but it's hard to say this stuff right all the time. For me, and I've been doing this for a very long time. It feels like a long time anyway, not as long as others. So then, if we go down to level 2, the random effects are U's, the same as usual. So U0IJ is the idea that I have a level 2 random intercept variance. U1IJ is the idea that I have a level 2 random variance in the level 1 time slope. These things are irrelevant. They're placeholders for what we just talked about at level 3. And then we come down here, beta 0, beta 1, beta 2, those are already been discussed, so the only new term then is E, which is the idea that I have a level 1 residual variance. So the new slide that I added, which we will get to at some point, has to do with pseudo R-square. So pseudo R-square is relevant when we are adding fixed effects or random effects, folks. Pseudo R-square is relevant when we're adding fixed or random. Fixed, yes. Because fixed effects explain variance, right? So we added the initial fixed linear time and fixed quadratic time, that's gamma 100 and gamma 200. And because time is a level 1 predictor, time and time squared explained E variance at level 1. Pair age is a level 3 predictor. It varies between pairs. So it has to explain some kind of level 3 variance as a main effect, more specifically, the one that's in its line. So the main effect of pair age is going to reduce level 3 random intercept variance. And because I have a random linear time slope at level 3, age by time is going to reduce the level 3 variance in the level 1 time slope. So E variance should stay the same because we're not adding anything at level 1. U0 variance should also stay the same because we're not adding any fixed effects at level 2. And U1 variance should stay the same because we don't have any interactions with level 2 by time. So here is what happens. So my reference person for my growth curve now is specifically a pair of twins who were 85 years old when they walked in the door. That type of person and their sibling has an average information test score, crystallized intelligence measure of 24 when they walk in the door. That's when time 0 is. They have an instantaneous linear slope at time 0 that is negative. That negative time slope becomes more negative by how much per year? And don't say 0.07. Twice. This is the twice. Yay, we got it. Twice the quadratic. So my new age terms then, you can think of those as moderators of the intercept and of the linear time slope. So for every year older you are when you walk in the door, your predicted outcome at time 0 is lower significantly by 0.86. So 0.86 per year of age, cross-sectional age. So people who are older when they walk in the door have a lower score. From there, we talk about this linear time slope is negative. What does age do to it? Which pattern is this? That's a more negative. So I've got a p-value of 0.0683. Are we going to call that significant or not? Any votes? Do we care? No? They're going to be hard? Okay, hard line. Unsignificant. How's that? That makes me cringe. Insignificant? That's even worse. That's like a value judgment. So we can still do the pattern, though. The linear time slope becomes more negative by 0.05-ish for every year older you are when you walk in the door. So older people decline faster-ish, but not quite. So on the whole, if I want to answer the question, does age matter? I'm using REML, so I cannot do a likelihood ratio test that compares models that differ in fixed effects to answer that question. But if I want a joint test of these two terms, that's a contrast. So I'm asking you to do one of these in your homework. I've done these periodically. So whether or not there are any what I'm calling trajectory differences, where trajectory to me means two terms. It means the intercept and the linear slope. I am referring to each of the two terms here. The effective age gets a 1 for its effect on the intercept. Its effect on the time slope gets a 1. Make sure you remember the comma. If you forget the comma, SAS doesn't understand that you're asking for a degree of freedom equals 2 test, and it will do it for 1 degree of freedom instead. Then it's not a multivariate wall test. I threw chi-score on here because that's what Stata provides, so I wanted to get you output that would be comparable. So here's my contrast statement. F times numerator degrees of freedom is chi-square. So they're giving you the same information on different scales. The difference in the p-value has to do with whether or not you're invoking denominator degrees of freedom. Chi-square assumes that you have infinite sample size. Chi-square is to z as f is to t. So if you want to report the p-value that goes with the f, you would also want to report your denominator degrees of freedom. And here are my pseudo R-square results. For once, this worked like it was supposed to. I love it when that happens in real data. So my intercept variance at level 3 went down by 7.8% because of the main effect of age. My linear slope variance for time, so this is the level 3 random variance in the level 1 effective time. That variance went down by 32%. Doesn't that sound like a lot? Do you remember what happened like a page ago? It wasn't even significant. It was only 7% of the total slope variance was at level 3. So I got 32% of the 7%, where the 7% was really not there in the first place, according to SAS. So I'm not sure whether to be excited about that or not, but it is what it is. Okay, now for the big finale, zygosity. MZs versus DZs, monozygotic versus dizygotic, identical versus fraternal. Can I say that? Is that okay? Okay, great. I can't pretend to be the geneticist in the room here, so I have to actually get it right, I think. So I'm adding 1, 2, 3, 4 fixed effects related to zygosity. This is not what people tend to care about in looking at heritability. It's all about the model for the variance, not the fixed effects. But I want to make sure that there's no differences by zygosity with respect to the fixed effects first, because if I don't do that, any comparisons about the variances are suspect. So I would not expect any differences between MZs and DZs, but I'm minding my P's and Q's, as they would say if you're old, and making sure, dotting T's, no. Dotting I's and crossing T's? Any other cliches I can give you? No? Due diligence. That's the other one I like. That sounds much better. So I'm adding these 4 terms right here. MZ versus DZ as a fixed effect on the intercept. MZ versus DZ as the modifier of the effect of age. MZ versus DZ as a modifier of the level 1 linear slope. And MZ versus DZ as a modifier on how age modifies the slope for time. That's a 3-way interaction, folks. Here is a contrast statement that lumps all 4 of those things together to say, does zygosity matter in terms of predicting information test? Surprisingly, yes. I didn't even make this up. So I'm using MZ versus DZ as a string variable here because I'm lazy, want to make sure that my labels show up in my output so I know what's what. Note who is the reference group here. That's the group that gets the zeros and the dots. It's the MZs because M is after D in the alphabet. It looks like DZs have a almost lower intercept, specifically among people who walked in the door at 85. There's no MZ-DZ difference in the simple effect of time. There is no MZ-DZ difference in the effect of age on the intercept, but there does appear, for reasons that I have absolutely no idea, to be that DZs have a more negative effect of age on the linear time slope. And I hemmed and hawed on that one because this one was positive and this is negative, which would make it less positive, but I know the difference is going to flip it into negative territory. And I asked for, did I ask for it? No, I didn't end up asking for it. I thought I asked for a contrast, but I couldn't remember if I did or not. And here are my pseudo R squares. The trajectory thing? Yeah, no, I was wondering if I asked for simple slopes for the MZ-DZ difference for this model, but I didn't. I'm just doing it off the top of my head. The trajectory thing is the set of those 4 effects. And individually, the only one that looked like it was significant by conventional standards is this one, but we also have this one here. And because of this interaction being significant, these other ones would move around as a function of centering. So I'm dumping them all into one pile to say, does it matter? That's not my interest in this case, but it's important to do this before adding variance differences. So the only term that looks like it changed appreciably the level 3 random intercept variance went down by 2.6%, and that is because of the main effect of MZDZ and the interaction of that with H. The other terms would have reduced the level 3 slope, but it actually went up a little bit instead. So now the grand finale. Yeah, here's my estimate statements. I'm like, I thought I did that. Yes, I did. I just didn't do it in that model. So spot the differences in the code other than that one. What am I adding to my syntax to be able to talk about heritability? There's one thing. There's one right there. Same idea elsewhere in the code. Yeah, Zolzig is here from before. We're also looking right here. Group equals Zig on all of my variance model lines, level 3, level 2, and repeated is now level 1. That is giving me separate estimates for everything in the variance model by zygosity. And I'm going to do a likelihood ratio test to compare that against the previous model. Yep. So that did help. Now, what the hell does it mean? So here's my breakdown. Trying to do all the math in front of you here. So the idea of heritability is to look at the difference in intraclass correlation between MZs and DZs. If MZs have a higher intraclass correlation, then that has to be because of genetic whatever, because otherwise the DZs would have been comparable. So we can differentiate how much of the intraclass correlations are due to heritability versus common environment, and then the remainder of the variance would be considered unique environment. So I have the results from the model that are relevant here for the intercept and the linear time slope. So we're talking about intraclass correlation with respect to each growth parameter, intercept and level 1 time slope. So here's my intraclass correlation for the intercept in DZs after allowing each group to have its own level 2 and level 3 variances and covariances. The intraclass correlation for the pair level is 0.437, whereas the intraclass correlation for the pair level in MZs is 0.85. So 85% of the intercept variance in MZs is shared relative to only 44% of the intercept variance in DZs. So if you do the rest of the calculations, heritability is twice that difference in intraclass correlation, which works out to be a heritability estimate of 0.83. Common environment then is the difference between that intraclass correlation for MZs minus the heritability estimate. That's 0.024, and then E is the remainder. So it looks like some of my formatting went awry here. I'll fix that later on. But that should be H squared. There we go. Now compare that in MZs. I got a level 2 pair variance, and I got level 3 pair variance and a level 2 pair variance. In DZs, the level 3 pair variance went to 0. So there's no shared variance in the slope in DZs. There is 31% shared variance in the slope in MZs. That's what we would expect if genetics matters. So the difference in intraclass correlation for the slope then gives us a heritability of 0.62. The math works out to be a negative effect of common environment, and then the remainder is E. So this is an example in which the estimates go out of bounds because of the particular numbers that were found, but it makes sense from the perspective of differences in intraclass correlation. MZs have more in common with respect to change. The fact that the slope variance at level 3 couldn't even estimate, though, gives me a little bit of pause in trying to make too much of these results. So here are my words then that describe all of that stuff. So, any questions? Yes. Oh, the contrast statement, where did that go? Is it here? No, it's from the previous model. The meaning of -1 and 1 is because zygosity is a class variable, so you have to give it a value for each of the possible values and describe that you want the difference between the two. It would just be a 1 if it weren't on the class statement. Yeah, -1 for one of the groups and 1 for the other gives you a net sum to 0. Yep. You need 3 values, and then you'd need 2 terms for each term, because you'd have 2 degrees of freedom for each effect. All right, other questions? All right, well then we do get to do the new example next week, which I'm very excited about. So let me know if you have any questions on homework. Otherwise, I will see you next week. Office hours start now.